Good evening, and welcome to a small, quiet corner of the night. You've arrived where time moves softly and thoughts loosen like lantern light across a calm room. Breathing finds an easy rhythm while the day waits at the door. Tonight we curl up with a gentle puzzle from the deep sky. If light cannot escape a black hole, how does gravity reach us so faithfully? We'll take it slowly, listening to space as it bends, feeling how motion follows those curves, and noticing the silent messages that travel even when light cannot. No rush, no strain, just the comfort of ideas unfolding at the pace of sleep. If these calm wanderings bring you ease, a quiet like and a soft subscribe, help others discover this peaceful place only when it feels right for you. For now, let the hush settle, let curiosity glow without glare, and allow your mind to grow light enough to drift. When you're ready, we'll begin. In 1964, a quiet paper by John Bell drew a thin line through our comfortable picture of the world and asked us to look again. The line was simple and sharp. If the universe is both local, no influence outruns light, and real things carry definite properties. Whether or not anyone looks, then certain patterns of correlation can never appear. Quantum theory predicts stronger patterns. Bell showed how to test that difference with numbers a detector could count. Years later, careful experiments kept finding the same soft but stubborn refrain. Nature does not fit inside local realism. The choice is uncomfortable. Either properties are not fully settled until a measurement nudges them into place, or the world's bookkeeping includes connections that outpace any signal we're allowed to send. The unease starts in a tiny stage set. Two particles are born together and fly apart. Their spins or polarizations or other quantum coins are entangled. Touch one coin here and the other, miles away, falls into coordination with it, as if the flips were rehearsed. It's tempting to think they carried secret instructions from the start, like two gloves packed in separate boxes. But Bell's inequalities rule out that cozy story. The statistics of real experiments overshoot the best a glove scheme can do. It isn't that we learn what was already there. The act of learning seems to help decide what there will mean. Not chaos, not whim, just a world where potential sits close to actuality, and measurement is the crossing point. That crossing invites a familiar doubt. Does something spooky rush between the particles faster than any beam of light to settle the books? The answer is gentler and stranger. Entanglement creates correlations no classical picture can mimic, yet it stubbornly refuses to carry messages. Set up any code you like. The remote outcomes will not bend to your intentions. On each side, the results look random. Only when notes are compared later, at light speed or slower, does the pattern ring out. The universe, it seems, allows harmony without whispering instructions from one instrument to the other. Influence, in the signal sending sense, keeps Einstein's speed limit. Relationship, in the quantum sense, is already woven into the score. Much of the disquiet comes from our words. Particle suggests a bead with a list of traits in its pocket. Quantum objects are more like lines of a melody defined by relations. Which note follows which chords fit, how the whole composition constrains the parts. Properties are context-bound. Ask the question one way, and the world answers in one key. Rotate the apparatus, and a different key becomes relevant. Between questions, the state is a set of weighted possibilities, what physicists call a superposition, neither here nor there, but truly poised. The wave function is the map of that poise. Whether the map is a picture of something real or a book of betting odds for our expectations remains one of the soft but serious arguments under the night lamp. Experimentalists, for their part, kept tightening every loose screw. They closed loopholes, ensuring that random choices of settings were made fast, that stray signals couldn't conspire, that detectors missed as little as possible, that distant stations were far enough apart for light to be late. The result, repeated in different labs, with photons, ions, superconducting circuits, even with cosmic light used as a randomizer, kept affirming the same understated verdict. Entanglement is part of the furniture. It isn't a trick of poor timing or hidden chatter. It's how the world keeps score at small scales and, by extension, how it quietly shapes the large. Then comes the old, tender question with new clothing. What is cause in such a world? We're used to billiard ball pushes. Quantum theory offers patterns of conditional expectation. If one detector clicks up, the other is likely to click down, given the chosen angles. Change the angles, change the likelihood. No knob on the first station can force a message into the second's readout. The ban on superluminal signaling holds, even while the joint statistics break classical bounds. It's as if space-time remains a faithful messenger no faster than light, while the deeper script that produces outcomes does not live separately in each place. The fabric is one thing. The patches are convenient for sewing. Science grows well in this soil of puzzled clarity. Progress here does not mean closing the book. It means learning which questions are fruitful to carry into sleep. The early quantum pioneers wanted a tidy picture, electrons orbiting like planets, light as a wave riding an invisible medium. The equations kept answering in a different accent. Wherever certainty tried to settle, a new phenomenon arrived with soft shoes, discrete jumps, wave-particle duality, complementarity, the uncertainty principle, tunneling through barriers you had no business crossing. Each surprise made the theory more predictive, not less, and yet each also pressed language to do kinder work. We started to speak of amplitudes, of interference, of operators that don't commute, tools that capture regularity without pretending to a view from nowhere. Bell did not end a debate so much as tidy the table and ask us to sit with what remained. Local realism was a comfort blanket. The data set it aside. What replaced it were families of interpretation, each with a way to cradle the same equations. Some say the wave function is everything and never collapses. Measurement is just the observer becoming entangled too, a branching of consistent stories. Some say there are extra variables hidden from us, but guiding outcomes, like currents under a river's surface. Some say the wave function is a powerful book of knowledge about potential experiences rather than a physical ripple in space. Others shift the focus entirely, insisting that what's real are the relations among systems, not their private inventories. None of these stories changes the counts in the detector. They change what kind of sleep the mind takes after the counting. Old philosophies find faint reflections here. Plato's forms and Aristotle's particulars echo in debates about whether the wave function is an abstract, real, or a convenient description tied to concrete events. In Buddhist thought, dependent origination speaks of things existing through relationships rather than essences. A cup is only a cup because of hands, clay, thirst, and use. Quantum mechanics hums a similar note. Properties bloom in context. The temptation to elevate mind to the center returns as well. If outcomes wait for observation, is consciousness doing the heavy lifting? Most working physicists smile and keep the bar low. A Geiger counter will do. Observation can be any irreversible record, any macroscopic trace that pries a single story from a garden of possibilities. Still, the question lingers like a quiet fragrance. Whether awareness is merely another physical process that joins the chain, or whether its presence shapes the chain's meaning, it helps to remember scale. Entanglement isn't a delicate butterfly that vanishes at a breath. It is robust enough to build technologies. Quantum cryptography leans on it to spot eavesdroppers. Quantum computers choreograph entangled states to explore vast spaces of possibilities in parallel, though noise and heat keep them humble for now. Even gravitational wave detectors, those patient rulers listening to spacetime's whisper, now use squeezed light, a quantum manipulation of uncertainty, to sharpen their hearing. The same strangeness that unsettles also serves, once given a steady bench and a careful hand. Meanwhile, another deep river runs nearby. Gravity, our day's larger question, wonders how a black hole, which traps light, can still share its gravity with the outside. That puzzle belongs to general relativity's geometry, not to signals beaming out from the dark. Mass and energy curve spacetime. Motion follows the curves. The whole does not need to send messages any more than a valley needs to push a river. The shape is already there. Yet when we ask quantum questions about that shape, what happens to information? How horizons behave when reduced to quanta? The two great frameworks begin to talk past one another. The most ambitious efforts to reconcile them become maps in pencil, tested first for inner consistency, later for touchpoints with experiment. One map proposes that the basic stuff is not points, but tiny strings whose vibrations sing out as particles. In that score, extra dimensions curl in small and silent, and certain paradoxes soften. Black hole entropy falls out with a satisfying clink in special cases. And a correspondence called AD-SCFT offers a dictionary between gravity in a bulk space and a quantum theory on its boundary, a hint that spacetime's interior might be a story told by entanglement at the edges. The successes are subtle and mathematical, real but remote from direct tests. Critics remind us that a great many possible vacua fill the landscape. Picking our universe from that choir is a challenge. Others work on loop quantum gravity or newer, humbler bridges that treat spacetime as emergent from networks of relation. All of these approaches keep the same bedtime rule. Do not outrun what experiment allows. Keep an ear tuned for a prediction the world can answer. When the mind tires of frameworks, return to the small room of experience. Two detectors in the dark, a coincidence counter-ticking, angles nudged by quiet motors, a logbook filling its lines. The numbers don't gossip. They rise above bells bound, flatten when the settings change, then rise again. Preference has no vote here, and that steadiness is a comfort. The universe is stranger than tidy models and more faithful than our fears. The gentlest way to live with this is to loosen the grip of either or. Signals stay local, correlations do not. Properties aren't decided until measured, yet the way they become decided is regular. Causality feels less like pushes and more like a score that fixes which chords may follow which. Daily life holds. Keys turn, coffee warms, stars keep their appointments. Quantum strangeness isn't a trapdoor under meaning. It's the deep architecture under the floorboards. If sleep arrives before the puzzle closes, that fits. Bell did not give an ending, but a standard of clarity. A way to sift stories the world will carry. Entanglement becomes a promise, intimacy without exchange, order without a patrolman. The moon is there when no one looks. A rounded solution of many relations, tides and photons, geometry guiding every fall. And if, Now and then, we ask the dark what is truly real. It answers as it always has, with patterns that hold, correlations that surprise, and an invitation to look again tomorrow. And if patterns are our compass, a quiet next step suggests itself. Perhaps the pattern isn't only in outcomes, but in space and time themselves. Following that thought, some explorers step into gravity's puzzle by treating space-time itself as something that can be counted thread by thread, stitch by stitch. In that spirit, loop quantum gravity pictures geometry not as a smooth sheet, but as a fine weave of tiny loops, a network whose links carry the minimum quanta of area and volume. At scales we can touch, the cloth feels continuous. Near the Planck length, it becomes beaded and granular, like frost on glass. In such a picture, the infinities that haunt traditional equation singularities at the center of black holes or at the very beginning of cosmic time soften into places where the weave changes pattern instead of tearing. A collapsing star does not hit a point of impossible density. The geometry resists, rebounding or transforming in ways that avoid a mathematical cliff. This approach has offered concrete proposals for how horizon areas come in discrete steps and how early universe expansion might pass through a bounce rather than a sharp birth. It even suggests small, testable ripples. Ultra-high energy light from distant explosions could spread ever so slightly, as if the fabric offered a faint grain to the passing wave. Astronomers watch gamma-ray bursts for precisely that sort of dispersion, though the night has been mostly quiet so far. The gentler troubles lie elsewhere. Recovering the full elegance of Einstein's smooth theory in everyday conditions is hard, and coupling that granular geometry to the rest of nature's cast electrons, quarks, the forces that braid them remains an unfinished song. Alongside that loom, other looms hum. Causal set theory imagines space-time as a growing ledger of elementary events ordered by cause and effect, a kind of cosmic family tree. Asymptotic safety looks for a stable fixed point in the high-energy flow of gravitational couplings, hoping that quantum corrections tame themselves. Emergent gravity sketches space-time as something like temperature or pressure, real and measurable, yet rising from deeper microscopic stories, the way warmth arises from molecules in motion. And in several lines of thought, geometry is woven directly out of entanglement, as if the closeness of places were a reflection of the closeness of quantum states. None of these frameworks is idle speculation. Each tries to meet the world halfway with hints that might be heard by detectors already on their marks. Gravitational wave observatories listen for signatures from the earliest seconds after the Big Bang. Subtle patterns in the cosmic microwave background could bear the stamp of quantum gravity's childhood. Even quantum processors, delicate as they are, may stumble onto behaviors that point toward principles we have not yet named. Sometimes, experiments answer directly. Sometimes, they merely narrow the field, the way a lighthouse sweeps fog and shows where the rocks are not. From the shape of space, it is a short, human step to the question of why this particular universe carries the fingerprints it does. The numbers that set the stage, the faint push of the cosmological constant, the charge and mass that tune electromagnetism, the ratios that let nuclei hang together, sit in a narrow range where stars can burn for long ages and chemistry can build delicate scaffolds like proteins and brains. Nudge them too far and the script falters. Galaxies don't gather, fusion can't settle, complex structures never get their chance. To some ears, that sounds like a riddle with a hidden answer. a sign that purpose seeped into the constants. To others, it simply reflects a quiet selection effect. Beings who can ask the question will only ever find themselves in a universe where the asking is possible. A wider stage sharpens that second view. If the laws naturally generate many domains, through eternal inflation's bubbling spacetime, or through a landscape of string theory vacua, or through a branching of quantum histories, then a census of possibilities becomes large enough that life's window, while still slender, is unsurprising. Critics reply that such explanations risk moving away from testability, trading "why these numbers?" for "these numbers are the ones you could see." Supporters answer that, if our best mathematics points to a generous ensemble, we should follow where it leads and let observations tell us which parts of the ensemble touch our sky. The conversation stays respectful in its best moments, because both sides are trying to keep faith with the same principle. Reality gets the last word, even if it speaks softly. The same softness reaches into the room where choice is felt. Quantum theory appears to include true indeterminism. Outcomes are not settled until measured, and no hidden notebook seems to dictate them in advance. It is tempting to tuck freedom into that openness, to say that where physics leaves a door ajar, will can walk through. Yet raw randomness is not what we mean by agency. A spin that falls up by chance is not the same as a hand that chooses. Many thinkers, therefore, fold freedom into a different fabric. What matters is whether actions flow from your character, your reasons, your web of values, in a way that would have gone differently if those inner threads were different. On that view, the coin flip of a neuron would not enrich responsibility. It would add noise. Still, the frontier invites bolder sketches. A few proposals tie consciousness to a special role in collapse, as if awareness itself prunes superpositions into single outcomes and thereby earns a causal seat at the table. Others suggest that the brain, warm and wet as it is, can barely keep quantum coherence long enough to matter. Evidence, for now, leans toward ordinary biology, doing the heavy lifting, with quantum effects present but not sovereign. The mystery of willing may live largely in levels of description, how patterns in matter become persons who own their choices, rather than in the throw of microscopic dice. Under the same night lamp sits probability itself. Quantum mechanics asks us to square amplitudes, the components of the wave function, to get chances of outcomes. The Born rule works with unfailing grace. Experiments affirm it again and again. Why that rule? And why probabilities at all, if some interpretations claim every outcome happens somewhere in a branching tapestry? Several paths try to make the rule feel inevitable. Decision-theoretic arguments say that a rational agent who believes in the branching should weight their expectations by the squared amplitudes to avoid sure loss bets. Symmetry arguments say that only the Born rule respects the deep invariances of the theory. Self-locating uncertainty says that before the branches have parted in your experience, there is a meaningful sense in which you do not know which copy you are about to be. Critics point out that premises can smuggle conclusions, or that counting branches is ill-posed when branches do not come in neat whole numbers. In more traditional stories, the rule is simply a bridge principle. It ties the mathematics to the frequencies of clicks, the way temperature ties kinetic energy to a sensation of warmth. Pilot wave pictures anchor probabilities in how often typical initial conditions wander through different regions of configuration space. Collapse models build them into the stochastic law that picks outcomes. The comfort here is not that one derivation has won, but that no derivation has spoiled the record. the rule keeps matching the world's steady drumbeat. Meanwhile, laboratories keep coaxing quantum behavior into places where classical expectation would have sworn it could not live. Antimatter, the mirror partners of familiar particles, forms interference patterns and entangled pairs as happily as ordinary matter, showing that the quantum rulebook does not play favorites. Cold atoms thrown into interferometers act as exquisitely sensitive clocks, feeling the difference in gravitational potential between heights as a measurable shift in ticking, a small marriage of Einstein's time dilation and quantum phase. In some experiments, a single cloud of atoms is placed into a superposition of being higher and lower at once, and each component accumulates its own proper time. When the cloud recombines, the difference appears as a phase that can be read out. Such feats do not yet unify gravity and the quantum, but they let the two shake hands in regimes where both leave fingerprints. Theoretical schemes imagine entanglement shared across horizons, or signatures of quantum hair in Hawking's faint glow, or delicate correlations that might encode how information escapes the fate of permanent loss. These remain sketches on thin paper. The practical hurdles are vast. Still, astronomers now read gravitational waves from colliding neutron stars and black holes, and those violent events carry the right mix of density and curvature to hint at quantum corrections if the universe is willing to show them. The cosmic microwave background, cool and almost uniform with tiny ripples, already remembers fluctuations, stretched from quantum sizes to galactic scales by early expansion. A still quieter trace could yet reveal more. Thread by thread, a pattern emerges that does not ask for sudden revelations. Geometry may come in grains that appear only under a microscope made of starlight. The constants may be the only ones we could ever have noticed, or one day they may fall from a principle we have not yet written down. Choice may keep its dignity without borrowing coins from quantum chance. Probability may stay a rule we trust because it keeps being true. And experiments, patient and precise, will keep walking into the dark with a ruler and a metronome, returning with results that neither flatter nor mock us, only guide us to the next piece of solid ground. If the mind grows drowsy while holding these threads, that is fitting. The universe is not a lecture hall. It is a vast breathing room where some of the furniture glows faintly and the rest waits until our eyes adjust. In that room, questions about the smallest loops and the widest multiverses can share a quiet corner. They do not need to be solved tonight to be worthy companions. And when patterns prove steady across places and times, a gentler question arrives. What quiet rule keeps them steady? Symmetry is that quiet rule, the way a melody keeps its shape even when the key changes. In quantum mechanics, the melody lives in Hilbert space, a roomy theater of possibilities, while symmetries act like slow turns of the wrist, shift a system in time, slide it in space, rotate it gently, and the score continues without a hitch. Emmy Noether's insight threads softly through it all. Every continuous symmetry brings a conserved quantity. Time translation hums and energy stays constant. Spatial translation walks with momentum. Rotational symmetry keeps angular momentum steady. In the quantum setting, these symmetries arrive as unitary transformations moves that preserve the length of the state vector, the way careful breathing preserves calm. Conservation here isn't an added rule, it's the echo of invariance. Some symmetries whisper even closer, touching the fields that stitch particles together. These are gauge symmetries, local dress codes for quantum fields, which say that certain changes of phase are physically nothing so long as a companion field adjusts in step. Electromagnetism blooms from the simplest version, the weak and strong forces from richer patterns with more colors in the palette. Whether these freedoms are mere bookkeeping or deep grammar is still an open, polite argument. But either way, they fence the possibilities so tightly that a single standard model explains a great breadth of experiments with startling accuracy. Equally tender is the idea that laws can be perfectly symmetric while the world that settles from them is not. A ferromagnet points in some direction even though the equations favored none. In particle physics, that preference becomes the Higgs field, taking a constant value everywhere, quietly giving certain particles mass as they move through that sea. The symmetry remains in the rules. The vacuum simply chooses a seat. From that choice, the W and Z bosons gain heft. Other fields stay nimble. What might have been a philosophical ornament became laboratory fact when colliders found the Higgs-like resonance and weighed it, showing how broken symmetry writes mass into the script without tearing the score. Follow symmetry long enough, and it leads to gentler puzzles about identity. Classical intuition gives every pebble a tag. This one, not that one. Quantum mechanics invites us to set the name tags down. Identical particles are not little individuals in a roll call. They are excitations of a field, and the mathematics treats them as indistinguishable. Exchange two bosons, and the wave function keeps its sign. Exchange two fermions, and it flips. From that small algebraic difference spring very different worlds. Bosons are sociable. Many can share a state building, lasers, superfluids, and superconductors. Fermions are reserved. Pauli keeps them from crowding, laying out the periodic table and the pressure that props up white dwarfs. In this light, individuality looks less like an essence and more like a convenient story that works when particles are far apart and interactions are gentle. Philosophy pads in on soft feet to ask whether two indistinguishable quanta can be different at all. If every qualitative feature matches, what remains to be the thisness of one electron versus another? A haxidist will say identity can float free of properties. An anti-haxidist will say such talk evaporates because nothing grounds the distinction. Quantum practice stays modest. It counts states, not persons. The statistics know what matters, and the detectors listen for patterns, not pedigrees. Still, the algebra's choice, symmetric here, anti-symmetric there, has visible consequences in spectra, currents, and the firmness of matter, reminding us that questions of identity in this domain are not only metaphysical poetry, but part of how the world behaves. The same discipline that quiets metaphysics fuels new tools. Quantum technologies live by coherence, the capacity of a state to keep its phases straight, by interference and by entanglement, which ties distant parts into one sentence. Protect those delicate structures from noise, and a different class of machine opens its eyes. A fault-tolerant quantum computer, guarded by error-correcting codes, could explore landscapes of possibilities that classical machines only circle from afar. Electron dances in complex molecules would be simulated directly, guiding the search for catalysts, drugs, and exotic materials. Hard optimization schedules, routes, designs with too many knobs might bend to hybrid strategies where quantum subroutines do the heaviest, most entangled lifting. Cryptography will change costumes too. Certain public key schemes, safe today, would crumble before algorithms that run best on these new devices. In their place, post-quantum methods are being readied to stand firm whether the attacker uses bits or qubits. At the same time, quantum key distribution flips the script by making eavesdropping itself detectable. Tamper with an entangled link, and the disturbance shows up as noise no spy can hide. Other instruments step softly into medicine and earth science. Quantum sensors use squeezed light and carefully prepared states to measure as precisely as uncertainty allows. Magnetic fields from a heart trace gases in a breath, mineral seams deep underground, faint shivers in space-time itself. Each becomes a little less invisible. Atomic clocks counting quantum ticks agree to so many digits that lifting one by a few centimeters changes its rate measurably. Arrays of such clocks can map the Earth's gravitational potential like a relief map. Searches for dark matter borrow quantum delicacy to listen for feeble nudges. The same strangeness that unsettles in philosophy becomes, in careful hands, a thermometer, a ruler, and a stethoscope. Every new power arrives with a pair of gloves, one lined, one bare. If large-scale quantum computers mature, before post-quantum defenses are widely deployed, stored secrets from yesteryear could be peeled open like old letters. Organizations will need to migrate, not only algorithms but also habits, how keys are stored, how long data is kept, where trust is placed. Quantum-enhanced sensing that peers through noise can save lives in diagnostics and disaster response. It can also raise questions when measurements reach through walls or past traditional barriers. Distributed quantum networks may blur the line between here and there, making locality feel like a design choice rather than a hard boundary. As engineers scale up entanglement, society will revisit familiar debates in new clothing. Who holds the keys? Who certifies the devices? Who gets to look and who gets to opt out? The prudent posture is simple and steady. Prepare early, verify often, and let excitement travel with safeguards. Across a century, the quantum theory itself has been a patient companion, steady in prediction, stubborn in interpretation. It computes odds with exquisite accuracy, from the Lamb shift of hydrogen to the magnetic moment of the electron, from semiconductor band structures to the acoustic peaks of the cosmic microwave background. Yet, when we ask what the formalism says about reality's furniture, the answers fan out into stories that share measurements and disagree about metaphors. Some picture a branching tapestry in which every outcome happens. Probabilities reflect how strongly each branch sings in the amplitude. Others keep a single world steered by hidden variables, with outcomes guided by a deeper flow that does not announce itself. Still others treat the wave function as a powerful book of expectations for agents embedded in the world, rather than a thing the world is made of. The experiments do not decide among these narratives. They keep time, and each narrative learns to dance to the same beat. Clarity may seep in from corners only now coming into view. Work that ties entanglement to geometry, hints that nearness in space-time may mirror the strength of quantum ties. Wormholes rhyme with entangled pairs. Holography suggests that a realm with gravity inside can be fully described by a quantum theory living on a lower dimensional edge. If even part of that song is true, then space looks less like a stage and more like a choir built from relationships. Complexity theory joins in, asking how hard it is to build certain states or unscramble certain patterns, and whether that hardness is not just a practical obstacle, but a law in its own right. The measurement problem may soften as decoherence, and quantum Darwinism explain how environmental interaction hides interference and promotes stable, widely shared facts. Pointer, states that many observers can read without tripping over one another. On this view, the quantum classical boundary is not a brick wall, but a fog line that moves with scale and context. Through all of this, symmetry returns like a refrain, demanding consistency, invariance, and mathematical grace has been a reliable way to find true statements about the world. It is tempting to believe that what we call our quantum theory is one island in a sea of allowable structures, singled out by symmetry principles and by the need for probabilities to behave and for signals to respect light's limit. Perhaps there are nearby shores we have not yet visited. For now, this island is a good place to rest. For tonight, the story is not that the riddle has been solved, but that we have learned to live with it fruitfully. We know what keeps. Superpositions matter in their consequences. Measurements create facts where only possibilities lived. Distant systems can share structure no local hidden script can supply. Probabilities follow the same squared amplitude rule wherever we probe. We know what remains tender, what the wave function is, where facts begin, how space and time might grow from entanglement. Between those knowns and unknowns lies a workable peace. Engineers shape devices that use the strangeness without bruising it. Philosophers keep the questions honest. Mathematicians groom the symmetries. Experimentalists ask the dark for one more decimal, and the dark, patient as ever, usually agrees. If sleep finds you while these thoughts are still turning, that fits the subject. Quantum mechanics has long been a companion for late hours, precise where it must be, mysterious where it should be, generous in the patterns it offers to gentler eyes. Whatever the final theory becomes, some graceful union with gravity, some emergent geometry, some language that puts information first, the steady lesson is already clear. The universe allows strangeness without losing order. It lets surprise in without letting us get lost. Under that promise, questions about symmetry, identity, and the tools we build from them can rest beside the pillow without demanding an answer before morning. And when morning comes to the same questions wearing a warmer coat, heat, time, and the tilt of irreversibility, it is the neighboring conversation that waits just beyond the door. Warmth and strangeness meet in a quiet truce when quantum theory shares a table with thermodynamics. One speaks in amplitudes and phases, the other in temperature, pressure, and time's one-way drift. On paper, they seem to disagree. Quantum evolution is reversible, unitary, like music that can run forward or backward without smudging, while the second law insists that entropy grows and cups of tea refuse to uncool. The reconciliation begins once we notice how much detail a macroscopic description deliberately sets aside. A state, like warm air in a room, lumps together an astronomically large family of microscopic arrangements. The phases and coherences that differentiate those arrangements are ignored. In that coarse view, information leaks into degrees of freedom we no longer track, and what leaks reads as rising entropy. Von Neumann's entropy gives this intuition a clean equation. Quantum information theory adds the accounting. Erasing a bit has a heat cost, Landauer's principle. Demons must pay their bills, and irreversibility reflects limits on control and knowledge rather than a fundamental tear in time's fabric. Even the arrow can wobble when systems are tiny and well isolated. Quantum thermodynamics studies engines with pistons made of energy levels and fuels made of coherence, where fluctuations are not nuisances but lawfully counted guests. Fluctuation theorems relate rare backward stories to common forward ones, Experiments with trapped ions and superconducting circuits have implemented miniature heat cycles and verified those balances. As systems grow and exchange whispers with their surroundings, decoherence spreads, phases blur, and the familiar march of entropy returns like a dependable tide. Classical behavior is not imposed from outside. It emerges as innumerable quantum details fade from our ability to control or even notice. Watching, in the quantum sense, is not passive. Measurement can slow change or spur it, depending on the beat. The quantum Zeno effect shows how rapid, repeated checks, "Are you still here?" can hold a state in place by continually interrupting the phase accumulation that would carry it elsewhere. Space those checks differently, and transitions accelerate, the anti-Zeno effect. Laboratories have danced through both regimes with atoms, ions, superconducting qubits, and spins in diamond. What begins as paradox becomes engineering. Error-correcting codes rely on frequent, gentle syndrome measurements that reveal noise without demolishing the computation. Quantum control designs pulses like cues in a score, steering systems along paths that natural dynamics would miss. In this choreography, observation is a tool, not a keyhole. A subtler departure from classical thinking hides behind the word context. The Kochen-Specker theorem proves that you cannot assign pre-existing, measurement-independent values to all quantum observables without running into contradiction. Outcomes depend on which compatible questions are asked together. The surrounding set of measurements matters. This is contextuality, and it has been tested with carefully crafted setups, from photons to trapped ions, closing off non-contextual hidden variable stories, much as Bell tests closed off local ones. Far from a philosophical oddity, contextuality fuels advantage. Certain quantum computations and magic state protocols gain power precisely by exploiting these context-sensitive correlations that classical systems cannot imitate. The world's answers are lawful, but the law includes clauses about how the question is framed. Step back, and a bolder idea gathers. Perhaps space and time are not the stage, but the chorus, emerging from patterns of entanglement. In the AD-CFT correspondence, our cleanest playground gravity in a bulk spacetime is exactly equivalent to a quantum field theory living on a lower dimensional boundary. In that dictionary, entanglement is mortar, not decoration. The Ryu-Takayanagi relation ties the entanglement entropy of a boundary region to the area of a minimal surface hanging into the bulk. Tier boundary, entanglement, and parts of the bulk geometry thin or disconnect, strengthen it, and regions draw closer. A slogan, ER equals EPR, goes further. A wormhole and an entangled pair may be two ways of pointing at the same underlying glue. These models are idealized, yet they whisper a possibility. Geometry could be bookkeeping for quantum correlations, and asking, what is space made of? Might be like asking what pressure is made of, an emergent regularity of many moving parts. Black holes, usually stingy with explanations, offer a different kind of compromise. Black hole complementarity proposes that no single observer can catch the theory contradicting itself. For the infaller, nothing special happens at the horizon. Local physics stays calm. For a distant watcher, information never crosses in. It smears along the horizon, scrambles, and later seeps out as Hawking radiation. Both stories are valid within their domains, and no one can compare notes to expose a clash. Push this logic, and tensions sharpen firewall arguments. Question whether the horizon can remain tranquil if radiation is fully informative, yet the core intuition holds. Quantum descriptions may distribute truth among observers without granting any one of them a God's eye view. In extreme regimes, what happened is not a single thread available to all. It is a set of mutually consistent accounts that no observer can unify in practice. The arrow of time looks different with these pieces in place. Decoherence doesn't just blur phases, it selects stable, widely shareable records. Pointer states that many observers can read without disturbing. Quantum Darwinism reframes this as environmental broadcasting. The surroundings make countless copies of certain properties, which then appear classical because they are redundantly stored. Reversing such diffusion would require erasing all those records with impossible precision. The second law thus reads as a statement about how information fans out into degrees of freedom we do not control, not as a lament about order decaying. All this theory bends back into tools and tests. Precision interferometry already blends quantum phases with gravity's pull. Atom interferometers measure time dilation across centimeters. Clocks lifted by a few inches tick detectably faster. Tiny engines turn coherent resources into work in the lab. Xeno-style stabilization holds qubits steady long enough to compute. Contextuality is no longer a footnote, but a resource to be counted in layouts of gates and codes. Even the entanglement geometry link leaves traces in solvable models that guide numerical methods and inspire error-correcting architectures that mimic holographic codes where boundary qubits protect an emergent interior. Throughout, the style of understanding changes tone. Classical explanation leans on trajectories, forces, and causes traveling along lines. Quantum explanation leans on structure and constraint, which patterns of correlation are allowed, which decompositions of a system are robust, which questions can be asked together. Thermodynamics then becomes a chapter in information theory. Energy and entropy are prices paid and credits earned in the economy of knowledge and control. Reversibility at the microscopic level coexists with macroscopic irreversibility because records proliferate and controllers are finite. Measurement becomes dynamical, an interaction that carves a branch of history and, if designed well, keeps fragile phases safe. Contextuality becomes both a limit on hidden bookkeeping and a lever for new computation. Spacetime itself starts to look like a ledger of entanglement shares rather than a pre-drawn grid. None of this unseats everyday reliability. Ice still melts, lasers still shine, GPS still works, because atoms keep time and relativity's corrections are exact. Complementarity doesn't make spacecraft trajectories fuzzy, it protects unitarity at horizons. Contextuality doesn't make a lamp undecidable, it makes certain algorithms powerful. Xeno effects don't meddle with heartbeats, they shelter qubits until the calculation is finished. The theories that play with emergent geometry still reduce to Einstein where we have checked, just as quantum thermodynamics reduces to the usual second law when many degrees of freedom share their secrets with the air. What remains is a mood of patient coherence. The same few ideas, superposition, entanglement, decoherence, information appear again and again in different costumes, and the costumes agree on what the instruments should measure. Entropy counts missing detail. Measurement can freeze or hasten change because probing is coupling. Values depend on context, and that dependency is not a flaw, but a feature with uses. Geometry may be the large-scale shadow of small-scale ties. Black holes may keep consistency by giving each observer a complete but non-overlapping story. It is a collection of quiet harmonies rather than a single high note. By this light, the bridge between quantum laws and thermodynamic habit stops feeling like a contradiction and starts reading as division of labor. Microscopic evolution is time reversal friendly. Macroscopic behavior is record-rich and forgetful in exactly the way that creates an arrow. Engineers learn to spend information to gain precision. Physicists learn to phrase questions so that context is an ally. Mathematicians sculpt the correspondences where areas become entropies and distances become mutual informations. Each craft strengthens the others. In the stillness of the room, the story holds together without hurry. Warmth as organized ignorance, observation as choreography, context as resource, and space-time as the wide, quiet shape cast by invisible bonds. From here, another question comes quietly into focus. If context steadies everything, who sets it when there is no outside to lean on? When the measuring device is the universe itself, the usual comfort of an outside observer fades like a shoreline at fog's edge. In laboratories, we can point to a clock, a detector, a notebook, things we agree to treat as classical. In cosmology, there is no clean outside. If everything is quantum, who does the measuring, and what counts as the apparatus? The Copenhagen habit, useful and tidy for small systems, begins to wobble when nothing stands apart. Other stories try to hold the frame steady. Many worlds keeps the evolution smooth and unitary. No collapse, only branching. Every quantum event in the young universe buds off histories, with probabilities understood as weights on those branches. The price is a delicate bookkeeping of meaning. What does likely describe when everything that can happen does? Consistent Histories offers another lamp. It speaks of decohering narratives, sequences of events that do not interfere with one another, and assigns probabilities to whole stories rather than to sharp measurements by external devices. Sets of such histories must be mutually consistent. Only then do the numbers behave. Each framework carries its own small unease. Choices about which histories to privilege or which coarse grainings to adopt can look arbitrary, and appeals to typicality can circle back on themselves. Cosmology does not cause these questions. It simply reveals them, because there is nowhere to hide the assumptions we make about observers and records. These worries splash against a more personal shoreline. People sometimes ask whether the most private fact we know, conscious experience, owes anything to quantum mechanics beyond the ions and electrons that any biology must use. Most neuroscientists answer with a practical shrug. The brain is warm, wet, and noisy. Coherent quantum phases tend to decohere there in unimaginably short times. That does not forbid quantum ingredients, but it suggests the relevant dynamics are largely classical at the scales that matter for thought. Bolder proposals do exist. One posits that tiny structures inside neurons, microtubules, host quantum superpositions, and that a special gravity-related mechanism tips them into single outcomes. With consciousness riding on the wave of that objective reduction, it is an inventive sketch, and yet evidence has not gathered in its support. The timescales look too short, the shielding too thin, the signatures too absent. Meanwhile, biology has surprised us elsewhere. Photosynthetic complexes seem to shepherd excitations with a touch of coherence. Migratory birds appear to sense Earth's field through quantum-sensitive chemistry. Some models of smell recruit tunneling to explain subtle differences between molecules. These are careful, local feats, nature using quantum tricks without keeping large swaths of brain tissue in a fragile superposition. The deeper puzzle remains open but quiet. Whatever consciousness is, we do not yet know which description, computational, dynamical, informational, carries the essential weight. Symmetry breaking offers a different kind of clarity, the way a flawless rule can yield a particular world. Imagine a perfectly round table and many chairs. The law says every direction is alike, but the first guest must still choose a seat. In quantum field theory, the Higgs field is that early guest. The equations treat certain directions in an abstract space as equivalent, yet the field settles on one, tiny but everywhere, and particles moving through it acquire mass. The W and Z grow heavy. The photon remains light. That quiet choice helps explain why electromagnetism reaches far, while the weak force fades quickly. Even though at high energies, both are faces of the same electro-weak unity. When experiments at a great collider finally heard the expected resonance in 2012, it felt less like a surprise and more like a confirmation that symmetry kept bent and sometimes broken truly governs the script. Early universe phase transitions likely used the same grammar. As the cosmos cooled, fields chose seats, and the choices may have left fossils. A slight excess of matter over antimatter, relic defects like
the ethereal
strings,
scroll reveals
even the fuel
arcs
for a
and
burst
soft
of
streaks
accelerated
of warm
expansion.
colors.
Each possibility ties a cosmic pattern to a simple principle. Rules can be symmetric, while outcomes are not. Quantum correlations have their own taxonomy, and entanglement is not the only citizen. Discord, a quieter measure, asks how much a joint state is disturbed when one side is locally examined. Non-zero discord means there are genuinely quantum correlations hiding in the structure of information, even when entanglement is absent. That realization complicates the once simple border between quantum and classical. Some computational advantages and communication tricks persist in states with discord, but no entanglement, suggesting that quantumness has layers. The debates here are technical but friendly. Which resource does the heavy lifting in a given task, and how do we count it? Whatever the final bookkeeping, the lesson is hospitable quantum benefits do not hinge on a single marquee phenomenon. The marriage of quantum mechanics with special relativity, quantum field theory, changes how we talk about particles. The field comes first. Particles are its excitations, like ripples on a lake. Creation and annihilation are not metaphors, but operators that add and remove quanta from specific modes. Even emptiness becomes lively. The vacuum is a structured state, with fluctuations that polarize charges, shift masses, and tug on mirrors in the Casimir effect. More strangely, the very notion of how many particles depends on who asks. An observer gliding smoothly through space may call it vacuum. An observer accelerating past will report a warm bath, a thermal glow where the first insisted on nothing, the Unruh effect. This observer dependence does not make reality fickle. It reminds us that particles are conveniences, while fields and their correlations are the sturdy furniture. The lesson also softens our grip on cosmic emptiness. Even what we call nothing can carry structure that leaves fingerprints on what we measure. Return once more to cosmic measurement with those lessons folded in. If there is no outside, probabilities must be tied to histories that decohere on their own, to records that become redundant in the environment, and therefore classical to many observers at once. In inflationary scenarios, tiny quantum jitters in an almost uniform field get stretched by expansion into the seeds of galaxies. The statistics imprinted in the microwave background are, in a real sense, fossilized quantum noise. Many worlds reads that fossil as one branch among many. Consistent histories reads it as one of the decohering stories our universe permits. Either way, prediction means computing the weights of outcomes we can all agree to read, not conjuring an external referee to shout, "Collapse." The lingering questions: how to ground those weights without circularity. How to pick the natural coarse grainings are honest and ongoing. They do not dim the empirical light. They shape how we place it on the nightstand. Across these topics runs a steady theme. Information is not decoration, but substance. Entropy counts missing detail. Decoherence turns possibilities into facts others can share. Discord and entanglement mark where classical bookkeeping fails. The vacuum's fluctuations alter what we measure. Symmetry breaking chooses a seat and thereby writes masses and ranges into the playbill. The hard problems, how to weight branches, how consciousness fits, how early fields chose their paths, remain gently unsolved. Yet the landscape is usable and kind. We can predict spectra, map anisotropies, cool atoms, calibrate clocks, build protocols that hide or reveal information with exquisite control. Cosmology and cognition may still keep some secrets behind a curtain, but the stagecraft out front is sure-handed and generous. If the universe is a single self-contained story, the narrator is shared. Histories that decohere enough to be told, records that spread through their environments, laws that stay the same under symmetries we test, and fields whose excitations we call particles when conditions are kind. The rest, the parts still debated, are interpretations of the same script read in different lights. That is not a flaw to be fixed before sleep. It is a shape the world makes when seen with instruments sensitive enough to catch whispers, but calm enough to keep from shouting over them. Small, concrete reminders help. The Lamb shift in hydrogen, a tiny nudge to energy levels, comes from the vacuum's restless fields. Between closely spaced metal plates, the Casimir force draws them together as modes are edited by the boundaries. Detectors on rockets and storage rings sniff at Unruh-like effects. While a clean observation is hard, the principle threads experiments and theory with a careful needle. Testing gravity's quantum grain asks for either mountains of energy or ears sensitive enough to hear a feather fall. Close to the Planck scale, where space and time would show their texture, our machines fall silent. The energies are far beyond earthly colliders, so attention turns to long baselines and long patience, tiny effects that could stack up across light years or centuries. Photons from distant gamma-ray bursts arrive in tight, brilliant flurries. If the rules of special relativity bend at extreme energies, the highest energy photons might be slowed by a hair, fanning the burst ever so slightly by energy. Astronomers sift those flashes for a telltale dispersion that would hint at a quantum-stitched spacetime. Gravitational waves give another path. The chirp from merging black holes carries phase information over vast distances. Minute quantum gravitational roughness might nudge those phases, leaving patterns a careful interferometer could read. In the lab, a gentler strategy asks quantum mechanics to betray itself, create superpositions of ever more massive objects, and watch whether gravity triggers a spontaneous collapse that ordinary theory forbids. Tabletop experiments have already placed dust grain-sized mirrors and clusters of atoms into delicate states. The frontier presses toward micrograms, even milligrams, where any deviation would be hard to miss and harder to explain away. Space is becoming a laboratory for such listening. Satellites watch the sky for cosmic rays and gamma rays. Constellations of detectors tune their timing to picoseconds. Future gravitational wave observatories will listen at lower frequencies, where supermassive black holes sing. Some quantum gravity ideas predict effects so small that even these instruments may never hear them. Others leave slivers of hope in spectral lags, polarization twists, or subtle noise in the space-time strain. There are parallel tracks as well, exquisitely cold atoms falling in Earth's field to test whether gravity entangles masses. Comparisons of atomic clocks at different heights, looking for departures from clean general relativistic redshift, microwave cavities, and optomechanical resonators, searching for the faint fingerprints of collapse models. Cosmology keeps a separate record book. The early universe was hot and dense enough for quantum gravity to matter, and the cosmic microwave background may still carry a scar of primordial gravitational waves or non-Gaussian patterns that points back to those first brief moments. The obstacle remains the same line on a chalkboard. The Planck mass stands 16 orders of magnitude above the best the LHC can do. Where brute force fails, ingenuity and integration times must do the work. Questions like these invite another, older conversation. What does it mean for a theory to be true? Quantum mechanics has earned trust the hard way by predicting numbers that match experiments down to astonishing decimals, yet its meaning is still argued under the lamplight. A realist hears an empirical triumph and concludes the formalism must be saying something correct about the world's furniture, however unfamiliar the furniture looks. An instrumentalist hears the same triumph and shrugs. The theory is a superb instrument for organizing experience, asking what really happens between preparation and detection is a misplaced demand. The measurement problem sits squarely between them. Realists want an objective account of how one outcome becomes actual. Instrumentalists are content to start the story at the click in the detector. Entity realists take a pragmatic side road, believe in what you can reliably manipulate electrons, photons, atoms and traps, regardless of metaphysical scruples. Structural realists move the faith one level higher. The relations and symmetries that survive theory change are what mirror reality best. The rest is scaffolding that may be replaced. Such debates feel airy until a new device forces a choice. Suppose future processors marshal millions of protected qubits and run for hours, exploring regimes where interference threads through depths no classical simulation can reach. If their performance ever deviates from quantum prediction in a systematic way, philosophy will suddenly have data. If not, confidence will expand to new scales. The same unitary rules holding firm from electrons to engineered objects made of trillions of atoms. Space-based tests may also push the envelope, entangle photons between satellites and ground stations across tens of thousands of miles, fly atom interferometers through stronger gravitational gradients, cross-check quantum phases against the sun's field. And on benches cooled to near nothing, levitated spheres and membrane resonators inch toward macroscopic superpositions. Any spontaneous collapse would stamp a frequency-dependent noise into their motion or leave heat in their baths. Biology, too, keeps a sidelong role in this story. Evidence already shows quantum tricks in photosynthesis and bird navigation. Efforts to spot similar threads in neural tissue remain speculative, but better microscopy and gentler probes may tighten the bounds. Most expect ordinary biophysics to suffice, with quantum effects as local helpers rather than sovereigns. Yet curiosity keeps the window ajar. However the future unfolds, some roots are deep. Quantum mechanics reshaped our ideas of causality and information by showing that possibility itself can be a calculable physical resource. Entanglement drew a border no local hidden variable map can cross. Superposition turned either or into a controlled both for now. Measurement, once assumed to reveal, became a process that also defines. Those are not temporary fashions. They are the grammar of phenomena, from atomic spectra to the cosmic microwave background's ripples. Yet, the way we talk about that grammar has a history, and it began in a room warmed by argument. In 1935, Einstein, Podolsky, and Rosen sharpened a worry. If quantum mechanics predicts perfect correlations between distant measurements, then either the world allows influence faster than light, or the particles carried predefined answers, hidden variables, when they parted. Einstein sided with local realism. Properties exist before they are read, and their effect outruns light. To him, the quantum account was incomplete, a brilliant tool missing a deeper explanation. The EPR setup is spare and persuasive. Two particles interact, then separate. Alice measures one, Bob measures the other, far away. The formalism lets Alice predict with certainty what Bob will obtain if he measures a corresponding quantity spin along a given axis, say. For Einstein, that certainty, without disturbance, meant the property had to be there all along. Otherwise, Alice's choice would reach across space and set Bob's outcome in place, which general relativity forbids. For decades, the paradox lived mostly in journals and conversations. Experiments couldn't yet speak to it cleanly. Time changed that. Bell found a way to translate the debate into inequalities any local realist theory must satisfy. Laboratories then built tests that closed loopholes. The results have been steady and clear. Nature violates Bell's bounds. Signals still obey light's limit. You cannot use entanglement to send a message faster than causality allows. But the joint statistics of measurements arise from relationships that no local script can emulate. The world is not arranged to soothe our classical intuitions. It is arranged to be consistent, generous, and sometimes delightfully resistant to simple pictures. That attitude guides the hunt for quantum gravity as well. We do not insist on answers where instruments cannot yet listen. We look for domains where different great ideas overlap and might disagree, a corridor between quantum theory's unitary evolution and general relativity's curved geometry. Gravitational waves serve as rulers, gamma-ray bursts act as clocks, superconducting circuits become quiet theaters where macroscopic superpositions can be staged. Each null result trims a branch of speculation and sharpens another. Each incremental detection, one more decimal, one more bound, adds a sturdy thread to the weave. Even absence is information. When photons from a distant flare arrive in step across energies, certain violations of Lorentz symmetry retreat. When a tabletop interferometer shows coherence, where a collapse model predicted none, parameters tighten. There is a patience to all of this that suits the night. We build the quietest rooms, polish mirrors until they hum with light's pressure, count clicks and detectors that have learned to whisper. We argue about what counts as real, while agreeing, scrupulously, on what counts as measured. We prepare for surprises without betting the house on them. Somewhere between the Planck length, too small to see, and the cosmic horizon, too far to touch, the clues we need are likely already present, folded into spectra and phases. ears, waiting for better ears. The work is slow, the questions are large, and the rewards are the kind that keep returning. Clearer patterns, kinder definitions, a growing sense that the universe can be both subtle and dependable at once. In the mid-1960 seconds, a soft-spoken note arrived in the long conversation that had begun with Einstein's worry. John Bell, working among magnets and beams at CERN, drew a boundary with math and invited the world to check which side nature preferred. If hidden instructions travel with each particle, and no influence moves faster than light, then the strength of correlations between far-apart measurements must live inside certain limits. Those limits, Bell inequalities, aren't opinions. They're the ceiling you get when outcomes are fixed in advance and distant labs can't whisper to each other. Quantum theory, with its superpositions and entanglement, quietly predicted that real experiments would push past that ceiling. A simple picture keeps the shape of the idea. Two particles are born together and fly apart. Alice and Bob each choose angles for their analyzers, polarizers for photons, spin axes for electrons, and record yes/no clicks. In any local hidden variable story, each particle carries a private set of answers for every angle Alice or Bob might choose. Compare enough runs, and the statistics can't exceed Bell's bound. But the quantum recipe doesn't hand out pre-written answers. It hands out a shared state. The numbers from that shared state overflow the classical ceiling with a grace that feels both calm and undeniable. One version has become a kind of lullaby in the field, CHSH, for the initials of Clauser, Horn, Shimony, and Holt. Choose two angles on Alice's side and two on Bob's. Then build a particular combination of four correlation numbers. Local realism says this CHSH sum cannot top 2. Quantum mechanics says it can reach 2. SQRT, 2, is approximately equal to 2.82. The difference is not decorative. It is the space where entanglement lives. Experiments routinely find values around 2.6 to 2.7 and, under clean conditions, skirt close to that quantum peak. The world seems to prefer the quantum melody. Early tests were delicate. In the 1,970 seconds, John Clauser and collaborators coaxed entangled photons from atomic cascades and compared their polarizations. In the early 1,980 seconds, Alan Aspect's group added a clever rhythm, rapidly switching analyzer settings while the photons were in flight to prevent any last-minute coordination by light-speed signals. Each generation learned to quiet a different doubt, and the inequalities bent in the same direction every time. The data didn't shout. It simply refused to fit the glove in the box story of prearranged properties. Skeptics, careful and needed, pointed to loopholes. Detectors missed many photons. If only a selected subset was counted, perhaps the result was biased, the detection loophole. Settings sometimes changed too slowly, or stations sat too close. A faint classical message might still sneak through the locality loophole. Through the 1,990 seconds and 2000s, experiments closed these gaps, one at a time. Better detectors for higher catch rates, faster random number generators for setting choices, longer baselines to enforce space-like separation. What remained was a wish for a single, decisive trial that closed everything at once. That wish was granted in 2015 when 3 independent teams performed what came to be called loophole-free Bell tests. In Delft, Ronald Hansen's group used electron spins trapped in nitrogen vacancy centers inside diamonds more than a kilometer apart, entangling them via photons and reading them out with efficiencies high enough to silence the detection worry, while random, ultra-fast setting choices sealed the locality gap. In Vienna and in Boulder, photonic experiments with state-of-the-art detectors and space-like separation reached the same conclusion. The violations were not tiny. Confidence levels soared, results quoted at more than 11 standard deviations, leaving almost no room for local hidden variables to hide behind imperfections. For this arc, from idea to instrument, Aspect, Clauser, and Anton Zeilinger were honored with the 2022 Nobel Prize in Physics, a public nod to a story that had already settled into the bones of modern physics. The conclusion sounds stark when written in daylight: give up locality or give up realism, but at night it feels more like a careful rephrasing. What's lost is the picture in which each particle carries a finished list of answers, and distant events remain merely coincident. What's kept is the structure of relativity that bans messages outrunning light. And that balance is not an evasion, it's a theorem. The no-signaling principle shows that, although joint statistics violate Bell's limits, no one can use entanglement to send a controllable signal. Bob's local data look perfectly random, no matter what Alice does. Only when they later compare notes the slow way, by radio, fiber, or courier, does the hidden harmony appear. Correlation without communication, structure without a causal shove. This is the place where words need handling like thin glass. Influence suggests a push through space. Non-local suggests a wire strung between labs. The safer view is relational. Entangled systems share a single description that does not factor into independent parts. That shared description fixes how their outcomes will agree or disagree when certain questions are asked. Nothing travels at measurement time because nothing needs to. The relevant ties were established when the pair was created. Relativity's prohibitions remain untouched because no knob at Alice's station can imprint a readable message on Bob's local stream of random results. The experiments themselves have a kind of bedtime steadiness. Two stations wake and sleep together in careful cycles. Random number generators in some tests seeded by distant cosmic light choose settings so late that even a beam at light speed could not coordinate them. Detectors count with near-perfect efficiency. Logs fill. Later, the data sets meet, and the telltale CHSH combination is computed. The number steps past 2, again and again, as calmly as a tide. When conditions change, angles rotated, timing shifted, the number responds, as the quantum recipe predicts. It is hard to mistake this for a fluke or a trick. Too many versions have sung the same tune. What follows from all this is as gentle as it is deep. Causality keeps its upper speed. Signals remain local, yet reality is not stitched from independent inventories carried by each object. It is stitched from allowed patterns of correlation, and those patterns are richer than any story with hidden, pre-written answers can allow. Some interpretations take that to mean the wave function is a complete, never-collapsing account, with measurement just entanglement spreading until an observer's record is part of the state. Others add variables that guide outcomes without permitting signaling. Others still treat the wave function as a map of expectations for embedded agents rather than a thing in the world. None of these choices alters the experiments. They are different lullabies for the same measurements. Even the technical details find use beyond philosophy. Quantum communication protocols rely on the same stubbornly non-classical correlations to prove that an eavesdropper has tampered. Device-independent randomness generators harvest the inherent unpredictability certified by a Bell violation. Networks that distribute entanglement over long distances test the same space-like separations that shut the locality door in the lab. The once paradox becomes infrastructure, a way of building systems whose security rests on nature's refusal to fit the local realist mold. It helps, finally, to notice the scale of the concession we are asked to make. Daily life does not stir. Coins still flip. Doors still latch. Planets still mine their ellipses. The revision arrives only where the world is quiet enough to let entanglement keep its form. And even there, it does not license faster than light whispers or time-loop mischief. It asks only that we trade a picture of separate, pre-decided properties for a picture of shared structure that reaches across distance. Under that trade, the facts remain kind. Experiments agree with theory to a degree that would make any other enterprise envious. And the old EPR worry, once a philosophical itch, has become a measured hue on the instrument's dial, a color we can point to and name. By the time the room is still, Bell's insight sounds less like a threat and more like a promise kept. The universe is free to be intimate without being irresponsible, to allow far apart things to belong to one description while keeping causality intact. That is not how we first learned to think, but it is how the numbers have taught us to listen. Picture the quantum state as a hush before a note many possibilities held in poise, each with its own amplitude, none yet chosen. The standard Copenhagen story says that this poised chord evolves smoothly by the Schrödinger equation until something we call a measurement happens. Then the hush tightens into a single note. One detector clicks, one value appears, one outcome becomes the fact that everyone can agree on. Between the smooth evolution and the sudden choice lies the crease that has bothered careful minds for a century. The equations never mention a special verb called collapse, and the theory never draws a crisp line between quantum things that can be superposed and classical things that cannot. We improvise the boundary in practice, treating our apparatus, our notes, and our logs as classical, and the method works astonishingly well. Still, the question lingers like a soft refrain. What exactly counts as a measurement, and why should the world need us to name it? Out of that refrain grew a small forest of stories that keep the same mathematics and change the furniture. One keeps the evolution everywhere and always. In Hugh Everett's view, there is no collapse at all, only one vast wave function that never tears. When a spin is measured, the device and the observer become entangled with the spin. The total state branches into mutually non-interfering records. Here, up, there, down. Each record is as concrete, for those inside it, as the weather. The randomness we feel is not a coin tossed by the universe, but self-location uncertainty. Which record will this version of me inhabit when the branching has run its course? The appeal is spare. No extra postulates, no mysterious moment where equations step aside. The hard work shifts to probability. Why should the weights we assign to branches match the squared amplitudes, the Born rule, rather than some other counting? Decision theoretic and symmetry arguments try to rebuild that rule from within the branching picture. Critics say the scaffolding sneaks in what it tries to derive. The conversation stays lively, and the lab results remain the same. Another path keeps the outcome, but adds a guide. In the pilot wave picture associated with de Broglie and Bohm, particles always have definite positions. Their trajectories are steered by a wave that obeys the Schrödinger equation, a guiding field that depends on the configuration of all particles at once. The non-locality is honest and explicit. What happens here can depend on settings there, though never in a way that allows faster-than-light signaling. Randomness is only ignorance of initial conditions. Given the starting point in the right distribution, the theory reproduces all the quantum odds. The comfort is ontological clarity, little things in motion pushed by a rule. The discomfort is its fit with relativity and with particle creation and annihilation in field theory, where the very idea of a fixed number of particles can blur. There are careful extensions and models that work in special cases, but the marriage to fully relativistic quantum fields is intricate, and many find the elegance of standard quantum mechanics lighter on luggage. A third route changes the law itself. Spontaneous collapse theories write the jump into the equation, adding rare, random localizations to the gentle wave evolution. The GRW model is the archetype. Each constituent of matter is subject to a faint, spontaneous hit that narrows its wave packet. For a single particle, the expected wait is fantastically long. But for an object with Avogadro's number of parts, the chances add up quickly, and macroscopic superpositions evaporate almost instantly. Cat-like states thus become ordinary either, or as without asking an observer to play midwife. This approach gives a clean explanation for why small systems can keep coherence while large ones cannot, and it makes predictions, tiny violations of energy conservation, faint noise sources that, in principle, experiments can chase. The parameters must be tuned to square with what we already know, and the theory accepts costs like that small energy leak as the price of a real collapse. Sensitive interferometers and levitated masses are learning to listen for exactly such signatures. A fourth view steps aside from ontology and talks about belief. In cubism, a quantum state is not the property of a system, but an agent's personal betting book about what they will experience upon taking certain actions. The born rule becomes a consistency condition that rational agents should use to update expectations. Collapse is not a physical event. It is Bayesian updating new information, new assignments. This dissolves many puzzles by refusing to reify the wave function and by letting different observers carry different state assignments without contradiction. The trade is a bold subjectivism that makes some uneasy. Science, they argue, should describe a world that does not depend on who holds the notebook. The cubist reply is that intersubjective agreement arises when agents communicate experiences and update. The formalism is a user's manual for experience, not a portrait of hidden furniture. Whether that stance is a retreat or clarification depends on one's taste for metaphysics. Threaded through all of these is the practical machinery that laboratories use every day: decoherence. A small quantum system rarely lives alone. It bumps and exchanges, whispers with a large environment, air molecules, thermal photons, a substrate. Those interactions entangle the system with many degrees of freedom and spread phase information into places no one will collect. In the reduced description we keep, off-diagonal terms in the density matrix fade. Interference between alternatives becomes astronomically hard to revive. Decoherence does not pick a single outcome, but it quickly selects a stable set of pointer states that behave classically and can be redundantly recorded by the environment. In that redundancy, facts become shareable. Many worlds leans on decoherence to explain non-interfering branches. GRW uses it to describe how collapse leaves robust records. Pilot wave dynamics reproduces the same classicality when effective wave packets separate in configuration space. Cubism treats it as the part of the world that makes certain expectations reliable. The same physics sits under many philosophies, steady as a heartbeat. Because the question is not purely mathematical, the tone matters. The measurement problem is less a single paradox than a cluster of rifts between words and equations. Outcome and process, observer and system, cause and correlation. Change which pair you try to reconcile, and you change which interpretation feels kindest. A spare determinist prefers the unbroken evolution of Everett. A realist drawn to particles prefers a guiding wave and definite paths. A pragmatist who wants a testable fix prefers GRW's tiny, random nudges. A Bayesian prefers to talk in terms of expectations and updates. None of these choices alters the interference fringes on a screen or the statistics in a Bell test. What they alter is the kind of sleep a mind can take after reading the logbook. The human question whether awareness itself plays any special role to stays in the room without raising its voice. Early, romantic suggestions that consciousness causes collapse have given way to soberer appraisals. A Geiger counter, a photographic plate, a memory register in a computer all are enough to make an outcome into a record. Decoherence theory, environmental redundancy, and the success of fully automated experiments argue that consciousness is not needed to fix facts. That doesn't solve the riddle of subjective experience. It only decouples that riddle from the mechanics of quantum measurement. The mystery of what it's like may live in neuroscience and philosophy of mind. The mystery of when outcomes happen can be addressed with Hamiltonians, couplings, and open system dynamics. Still, there are bridges between the formal and the felt that make the topic gentle to sit with. In every workable account, measurements are interactions that create correlations between a system and an apparatus, and usually an environment. Where those correlations are sharp and redundant, many observers can agree on a result without undoing it. Where those correlations are delicate, the world keeps options open and interference can appear. The classical quantum boundary is not a wall, but a zone of practice, defined by scales, temperatures, isolation, and the patience of the experimenter. Move slowly and carefully enough, and even large systems can be coaxed into showing their quantum face. Add noise and warmth, and even small systems behave classically. Meanwhile, experiments that press on the crease continue to refine our intuitions. Superconducting qubits are measured gently, with weak, continuous monitoring that lets one watch a quantum state diffuse and then settle. Quantum non-demolition readout preserves certain observables so they can be read again without disturbance. Interferometers place mirrors made of trillions of atoms into states where a single photon matters, then read them with squeezed light to limit measurement back action. Molecules with dozens or hundreds of atoms are sent through gratings to draw interference fringes, extending superposition into shapes we once assumed were too large. Proposals to test collapse theories with levitated spheres, or to compare GRW-like predictions against precise heating rates are becoming practical. Each success teaches the same old lesson in a new key. Outcomes are not pre-written on objects. They are written in correlations that measurement creates and that environments then protect or erase. In the quiet of a late hour, it's possible to hold more than one of these pictures at once, not as truths competing for a crown, but as lenses that keep the math steady and change the metaphors. The equations remain the anchor, unitary evolution for closed systems, probabilities given by squared amplitudes, correlations bounded by the no-signaling principle, and yet strong enough to defeat local hidden variables. Around that anchor, different stories make different promises. One offers a single, deterministic world with many narratives that never meet. One offers definite particles guided by a holistic wave. One offers a small, lawful randomness that hardens possibilities into facts. One offers a manual for consistent expectations without metaphysical baggage. The right choice, for now, is the one that helps you keep the music slow and the logic clean, while the instruments do their work. There's a venerable idea that the chain of measurement can't go on forever. John von Neumann followed the mathematics to a cliff edge. If system, apparatus, and environment all obey the same quantum rules, the entanglement just keeps spreading. Somewhere, the bookkeeping must switch from both at once to this one, not that, he suggested. The cut might live where experience lives at consciousness. Eugene Wigner dramatized the worry with a story. His friend inside a sealed lab measures a particle and writes down the result. Outside, Wigner treats the entire lab, friend included, as a single quantum system still in superposition. Two descriptions, both lawful, apparently disagree. To mend the tension, Wigner first floated the bold cure. Conscious awareness collapses the wave. Later he softened, but the parable stayed, and modern Wigner's friend variants multiply the observers and the layers, showing how different witnesses can assign incompatible quantum states to the same physical setup without any one of them catching the contradiction. Either consciousness does something special, or facts are not the same for everyone, or the story we tell about measurement needs a gentler grammar. Most working physicists prefer the gentler grammar. Consciousness, they argue, is not a magic solvent for superpositions. The practical cure is decoherence. Real systems are never alone. Photons, air molecules, phonons, in a solid, a warm bath of infrared light. These countless degrees of freedom interact with the system and carry away the delicate phase relations that enable interference. The total state remains pure, but for anyone who ignores the environment, which is everyone. The system looks mixed and classical, with probabilities that add rather than amplitudes that weave. The timescales are brutal. For macroscopic objects at room temperature, the off-diagonal terms fade in femtoseconds or faster. That is why chairs don't diffract and cats don't blur. Decoherence also picks favorites. Positions couple strongly to the environment, so where decoheres quickly. Certain combinations of states, the pointer basis, are stable and get redundantly recorded. You and I can check them without erasing them. Even so, decoherence does not by itself pick one outcome. It explains why interference vanishes and why many observers agree on robust records. It does not explain why a single record is experienced rather than a superposition of records. That last step is supplied by the interpretive layer you prefer. Many Worlds says there is no single record. The records have parted ways so thoroughly that they are effectively separate histories. Pilot Wave says particles already had definite positions. Decoherence just explains why wave packets separate and don't overlap again. Spontaneous collapse models add tiny random jolts to the law, making one record actual with a probability equal to its squared amplitude. Cubism says record is a word about an agent's experiences and updates. On the ground, the experimental ritual is the same. Above it, the metaphors differ. While the foundations simmer, engineers treat superposition as a resource to be cultivated and guarded. A qubit is a tiny space where 0 and 1 can coexist with a controlled relative phase. Array many qubits and entangle them, and you have a machine that explores structured possibilities in parallel. Proof of principle processors, superconducting, trapped ion, photonic, have already done calculations that would take classical machines a very long time to imitate, if at all. The headline-grabbing demonstrations are less important than the steady march beneath them. Longer coherence times, cleaner gates, lower error rates, better calibration. The headwind is always the same: decoherence and noise, which push quantum states back toward classical mixtures. Quantum error correction answers with a kind of chorus singing. Encode one logical qubit across many physical qubits. Measure gentle syndromes that reveal where errors nibbled without collapsing the information you care about. Correct, repeat, and keep the melody intact. The threshold for full fault tolerance is demanding, and the overhead is large, thousands of physical qubits for one quiet, logical one. But progress is real, methodical, and inventive. Entanglement does more than compute, it secures. Quantum key distribution uses the impossibility of perfectly copying unknown states to guarantee that an eavesdropper leaves fingerprints. Try to intercept and resend, and you add errors the legitimate parties can see. Satellites have already stitched entangled links over continental distances, showing that a global quantum network is not science fiction, but an engineering problem. In such a network, quantum teleportation moves states, not matter, by combining entanglement with ordinary communication. Nothing outruns light. No signal sneaks past causality, yet the state reappears at the other end with fidelity that only entanglement can support. The name is theatrical, the physics is restrained and exact. At the same time, experiments keep nudging the border between whisper and shout. Interference has been seen with molecules rich enough to deserve nicknames. Optomechanical devices place vibrating membranes and levitated beads into delicate states, reading their motion with squeezed light that trims measurement noise. Proposals aim higher: superpositions of objects near the microgram scale, matter wave interferometry for nanoparticles, comparisons of heating rates, and spectral lines sharp enough to detect the faint noise that some collapse models predict. Far away, gravitational wave observatories listen for spacetime's tremors with rulers so precise that quantum backaction must be tamed. Future versions may be able to hear tiny quantum fingerprints in the way those waves phase as they travel. Closer to the bench, ultra-cold, ultra-clean setups approach the limit where the environment truly has little to say, letting coherence last long enough to run delicate tests of the theory's edge cases. Even the Wigner's friend family of experiments has found careful, modest embodiments. Researchers build nested observers, small quantum systems that play the role of friends, and show how, depending on when you open the box and how you ask the question, different, self-consistent accounts can be written for the same sequence of interactions. No one is claiming contradictions you could watch with your eyes. Rather, the point is structural. Quantum theory allows assignments of states that are relative to the information held by different observers, and pushing that relativity too hard with classical words makes paradox-shaped shadows. Decoherence and the practicalities of measurement keep us safe in the lab. The puzzles live mostly in the space where language tries to compress the formalism into everyday intuitions. Through all of it, the human-tinged idea that consciousness causes collapse has faded into the background. Not because consciousness is uninteresting, But because the places where quantum theory touches the world most delicately, ion traps, Josephson junctions, cavity QED, already make definite, repeatable facts without a person paying attention. Photons expose plates, currents flip bits, detectors log clicks deep in shielded racks at 3 in the morning. What awareness does with those facts is another mystery entirely, one that neuroscience and philosophy are still courting. But the creation of the facts themselves, turning a field of possibilities into a stable record, seems to be a matter of interaction, amplification, and redundancy, not of being witnessed. It's useful to notice how often the same cast of ideas returns. Entanglement weaves systems together. Decoherence loosens the weave where the environment pulls. Error correction retightens it deliberately. Measurement is not peaking, it is coupling and amplifying until a trace is robust in many places at once. Preferred bases emerge from the pattern of couplings, not from decree. And when we ask the theory to explain why this one outcome, we find different, compatible roads that share the experimental mile markers but post different signposts for the mind. That plurality bothers some and relieves others. The instruments are agnostic. They hum to the same equations. Meanwhile, the frontier where quantum meets gravity keeps beckoning. If collapse is real, ultra-precise interferometers and levitated mass experiments may catch its hiss. If gravity itself participates in entanglement, exquisite tests with massive, cooled oscillators could show it by revealing phase relationships that only a quantum mediator can imprint. If nothing new happens, and quantum theory keeps its poise up to larger and larger scales, that too will be a powerful answer, one that narrows the landscape of viable ideas and shifts our courage to other corners. For quiet rooms like this one, perhaps the kindest way to hold the topic is to keep the hierarchy straight. The mathematics tells us how possibilities evolve and how to assign odds. Decoherence explains why certain states thrive as records. Interpretations tell us what kind of story to tell ourselves about outcomes. Technology builds little theaters where those stories can be tested and already harvests practical gifts from the same strangeness. Consciousness does not need to rescue physics, and physics does not demote consciousness. They pass each other in the hall and nod, still on speaking terms, still working out what to say next. Time, in quantum theory, is a quiet outsider. Space gets operators you can measure. Time arrives as a parameter in the margins, a label that tells the Schrödinger melody how to flow. That asymmetry sits uneasily beside general relativity, where space and time marry into a single fabric and geometry itself becomes dynamical. Ask quantum mechanics for an uncertainty relation for time, and it shrugs. Ask relativity whether clocks in different places agree, and it answers with tidal nuance. Bring the two together, and the questions thicken. Is a quantum measurement instantaneous, a clean snap from many possibilities to one? Or does the settling take a small but real span? If everything evolves unitarily when isolated, what clock keeps that evolution for the universe as a whole when there is no outside to count the beats? Push the union harder, and you reach equations where time quietly leaves the stage. The Wheeler-DeWitt equation, a proposal for the wave function of the entire universe, has no explicit time at all. It speaks of a landscape of geometries and matter fields in superposition, mountains and fields, photons and dust, but no ticking parameter keeps score. One answer, offered by Page and Wooters, is to build time from within. Choose part of the universe to be a clock, and let correlations with that clock define what before and after mean for the rest. In this relational view, evolution is a pattern of entanglement. When the clock says later, other subsystems show the correspondingly shifted states. Experiments with entangled photons and atomic clocks have begun to play with this idea, showing how time dilation appears even when clocks themselves are placed in delicate superpositions of height or speed. The effect is gentle, but it is there. Quantum clocks feel gravity's stretch just as classical ones do, and phase becomes a meeting point between the two worlds. Black holes pull these questions into a darker register. Hawking's calculation showed that horizons are not perfect one-way doors. They glow with thermal radiation and shrink, a slow evaporation that would, in principle, end with the hole gone. The radiation looked purely thermal, as if it remembered nothing of what fell in. Taken literally, that would mean information is destroyed, and the elegant unitarity of quantum mechanics would be broken. The paradox has sharpened over decades, and each sharpening has taught us something about the grammar of entanglement. Complementarity proposed a peace. The infaller sees nothing strange at the horizon, while the distant observer sees information smeared, scrambled, and returned in the radiation. No one can check both views at once, so there is no contradiction in practice. Then the firewall argument pressed harder. If late-time Hawking quanta are entangled with early radiation to carry information out, they cannot also be entangled with partners behind the horizon in the way a smooth vacuum requires. Something must give unitarity, the equivalence principle, or the quietness of the horizon. A different current offered a surprisingly bright rope: holography. From black hole entropy, the rule that a horizon's information scales with its area, not its volume. Gerard, Hooft, and Leonard Susskind drew the suggestion that all the information in a region can be encoded on its boundary. Maldaceno's Add CFT correspondence turned suggestion into dictionary. A quantum gravity theory in a certain curved spacetime is exactly equivalent to an ordinary quantum field theory without gravity living on the boundary. In that language, black hole evaporation is manifestly unitary. Everything that falls in has a boundary description that never loses track. The Ryu-Takayanagi formula and its descendants made the connection precise, tying the entanglement entropy of a boundary region to the area of a minimal surface in the bulk. Geometry becomes a book of correlations. Cut the book's pages, and you change the shape. The firewall debate drew nourishment from this soil too. If entanglement knits space together, then perhaps maintaining unitarity requires the horizon's interior to be related to the exterior in a way that looks drastic in semi-classical terms. ER equals EPR, a speculative slogan, suggests that entangled pairs and wormhole connections are facets of the same underlying relation, so that where information lives is a subtler question than classical geometry implies. Another line of work sees space-time itself as a quantum error-correcting code. Bulk information is redundantly stored in boundary degrees of freedom, robust against localized noise. In that picture, the smoothness of a horizon is a property protected by code structure until enough radiation has been collected to reconstruct what fell in. None of these sketches is the last word. They are working maps that have already guided calculations showing how information could, in principle, be recovered from Hawking radiation without violating causal order. Cosmology gives a kinder vantage point on quantum influence. In the first fraction of a second, inflation is believed to have stretched tiny quantum fluctuations into classical seeds. The same formalism that predicts interference fringes on a bench predicts the fine, nearly scale-invariant ripples we see in the cosmic microwave background. Those temperature variations, measured with exquisite precision, carry the signature of quantum randomness, broadened by expansion, and their statistics match the predictions astonishingly well. It is a quiet triumph. The positions of galaxies trace the frozen echo of ancient quantum jitters. Here, too, the measurement problem casts a soft shadow. What collapsed those primordial superpositions into definite density patterns? Decoherence by gravitational and matter couplings is the modest answer. As modes stretched and interacted, their phases became a matter of record in many environmental degrees of freedom, and each region of space settled into a classical description for all practical readers. Many worlds interprets this as branching cosmological histories. Other views supply different endings to the same overture. The data are the data, and they favor inflation's story told in quantum terms. Ask more of beginnings, and the questions become speculative but sincere. The Wheeler-DeWitt wave function invites boundary conditions. Hartle and Hawking proposed no boundary, a path integral over compact geometries that gives the universe a smooth start without an initial edge. Penrose imagines a more cyclical grace, aeons that expand and thin until, in a conformal sense, the cold, dilute future of one becomes the hot, dense beginning of the next. Each option wrestles with the same themes: how probabilities are assigned without an external time, how typicality is defined when the universe is the only sample, what it means for a quantum state to be a cosmos. None of these ideas asks to be believed as doctrine. They ask to be weighed for coherence, for calculational power, and for the small, specific fingerprints they might yet leave. Meanwhile, on more modest scales, time remains a physical resource that can be shaped and counted. Quantum clocks are built from transitions that tick with such regularity that lifting one by centimeters changes its rate measurably. Interferometers place atomic wave packets at different heights simultaneously. Recombination reveals the difference in proper time as a phase. These experiments seat relativity and quantum mechanics at the same table, and the table holds. They also feed back into the foundations. When clocks are quantum, questions about instantaneous collapse are replaced by questions about how correlations spread, and when records become redundant enough to deserve the title fact. The overarching moral is both tender and strong. Quantum theory is not a set of occult claims about the world refusing to decide. It is a precise tool for tracking how possibilities flow into structured facts, under constraints that respect causality while allowing relationships stronger than any classical story provides. Relativity is not a demand that nothing interesting connects distant regions. It is a rule about how influence propagates and how clocks compare. In the overlap, we learn to be careful with words like when and where, because entanglement can make those answers relative to the questions asked and the records kept. Holography and error correction teach that locality may emerge from deeper algebraic ties. Cosmology teaches that the largest structures we see were once quantum whispers. None of this unsettles the reliability of the world we wake into. A kettle still cools. A GPS receiver still trusts its satellites. A pulsar still keeps time for 1 billion spins. The puzzles live where they belong, at horizons in the first instance, in equations written to describe the everything that contains the writer. There, time sometimes hides and sometimes emerges. Information sometimes seems lost and then finds a different route home. We are learning to read these behaviors not as contradictions, but as invitations to change the level of description. What looked like a missing clock may be a correlation we hadn't counted. What looked like a disappearing bit may be a code word we hadn't learned to decode. If the mind grows quiet while holding these threads, that is fitting. Time in quantum mechanics is not a metronome, but a relationship. Black holes are not just voids, but laboratories for information. The early universe is not a murky myth, but a measured echo of lawful noise. Step by step, the theories that seem to talk past each other begin to rhyme. The rhyme is not finished, but it is audible. Geometry from entanglement, entropy from area, clocks from correlations, history from records. It is enough, for now, to hear the pattern and trust that careful questions asked under a calm lamp will keep bringing the next verse into focus. Questions that once sounded like riddles now feel like steady companions. What is real when no one looks? What counts as a cause? What makes an explanation more than a recipe that works? Einstein's moon there, whether watched or not, stood for a certain kind of comfort. Quantum mechanics trimmed that comfort and offered a subtler promise. What we can say about a system depends on how we ask, and different ways of asking reveal complementary faces that refuse to merge into one picture. In this mood, measurement is not a camera flash, but a specific kind of interaction that yields a record. Bohr's complementarity is the grammar of those records. Interference here, sharp positions there, never both at once. To some ears, this sounded like surrender, a step back from truth toward mere bookkeeping. To others, it was a wiser honesty about how knowledge is made. The long echo of those early debates reaches into current philosophy under gentler names. Realists keep faith that successful theories latch onto the world's furniture, even if our catalog is provisional. Instrumentalists keep faith with prediction and control, wary of metaphors that outrun what can be checked. Between them stand structural realists, who notice that relations and symmetries survive. Theory change better than the imagined things that carry them. If the scaffolding that endures is the web of allowable correlations, perhaps structure, not substance, is the bedrock. Push that view further, and you arrive at ontic structural realism. Patterns are primary. Objects are convenient abbreviations for nodes in a persistent graph of relations. The cautionary chorus answers with history. Yesterday's theories felt inevitable too, yet quantum mechanics keeps earning credit, unifying chemistry and electronics, sharpening astrophysics, surviving every measurement we can contrive. So the modest realist concludes that, at the very least, we are orbiting the truth. Mathematics sits at the center of this calm storm, not as decoration, but as the instrument that makes the music possible. Complex numbers, operators on Hilbert spaces, groups that encode symmetry, these are not folk charms, but working parts. The imaginary unit, E, never shows up on a dial, yet equations that keep it close predict phenomena to absurd precision. Some take this as a hint of Platonism. Mathematics is discovered, not invented, and the world participates in its timeless forms. Others prefer a grounded view. Math is our best compression scheme for patterns the world offers. Its unreasonable effectiveness reflects something about the world's regularities and something about our selection bias for tools that work. Whichever story one favors, the consistent lesson is practical. When the math is elegant, constrained, and generous in consequences, physics tends to be healthy. When the math is baroque and underdetermined, physics asks for a better melody. The horizon ahead is busy and quiet at once. Quantum processors grow by careful increments, qubits made steadier, gates made cleaner, errors made rarer. If coherent devices reach the scale where millions of qubits work together under error correction, entirely new regimes of the theory will be exercised, not as metaphors, but as hardware. Should those machines behave exactly as quantum mechanics predicts, confidence will extend to size and complexity beyond anything seen in nature. Should they misbehave in a specific, repeatable way, that crack will be the first reliable clue that the theory needs deepening. Orbital platforms will add their own experiments. Entanglement distributed across thousands of miles. Interferometers drifting in microgravity. Quantum links tested under solar wind and cosmic rays. Each setting quiets a different noise, shining light into corners that terrestrial labs leave dim. These advances will not only test interpretations, they will shape new questions. Quantum field theory in curved spacetime already shows how vacuum is not empty when horizons are near. Quantum information has taught us to count entropy geometrically and to see error correction hiding in the way bulk and boundary speak to one another. As those languages mature, what is spacetime becomes a question about how correlations knit locality and how codes protect smoothness. The old divide between foundations and applications softens. Building a quantum repeater or designing a fault-tolerant gate is not separate from understanding measurement. It is measurement, made domestic and reliable. Beyond physics proper, quiet revolutions are underway. Photosynthetic complexes steer excitations through tangled networks with efficiencies that look like art until the quantum details are noticed. Birds appear to read Earth's field using radical pairs, whose spins evolve coherently long enough to make a difference. Smell may sometimes rely on tunneling-assisted discrimination. None of this turns the brain into a grand quantum computer, and most neuroscientists remain happily skeptical of such leaps. But the lesson is generous. Life can shelter coherence long enough to be useful, even in warm, wet niches. Evolution is a patient engineer. Instruments built from the same grammar are changing what can be sensed. Atomic clocks, counting transitions as regular as morning, now notice when they are lifted by a finger's breadth. The tick slows or speeds by a part in 10, 18, letting gravity write its small slant directly into time. Magnetometers measure whispers from heart cells and the faintest trace gases. Interferometers use squeezed light to reach below the noise one observable would otherwise impose. In these devices, the uncertainty principle is not a barrier, but a map. Move noise from here to there, reduce it where it matters, accept it where it does not. Precision becomes an art of trade-offs guided by theorems. Meanwhile, the old philosophical themes keep breathing. Does the world possess properties independent of questions? Or are properties ways the world answers to particular couplings? Is explanation a mirror of mechanism, or a scaffold that predicts and controls? How much belief should we invest in entities versus patterns, in ontologies versus structures? The best posture is neither defiant certainty nor agnostic drift, but a practiced curiosity. Prefer accounts that are testable, minimal, fertile. Stay ready to trade metaphors when new data ask for new ones. Quantum mechanics rewards that posture. It refuses to be one thing because nature refuses to be one note. There is comfort in the way disparate strands rhyme. The same squared amplitude rule that predicts a photodiode's click also shapes the ripples in the microwave background. The same entanglement that frustrates local hidden variables also helps knit bulk geometry from boundary data. The same decoherence that makes cats classical also stabilizes sensor readouts and quantum memories. The same complementarity that tells us not to chase which path information and interference at once also guides designs that preserve coherence while extracting what we need. When different crafts reach for the same small set of ideas and find them sufficient, confidence grows. Perhaps this is the most humane gift of the quantum story. It asks us to live with layered truth. At breakfast, realism serves well. The coffee is in the cup, whether or not you look. At the bench, instrumental discipline keeps experiments honest. Define the preparation, specify the measurement, count the clicks. In the seminar room, structure earns respect, symmetries, constraints, conservation laws that govern what any ontology must fit. In the long evening when the room is still, humility returns. There are good competing ways to tell the same reliable tale, and it may be that what is real is partly a question about what kinds of patterns endure. As for the moon, a kinder answer now suggests itself. It is there not as a secret list of properties carried under its skin, but as a stable knot in many relations: tidal pulls, reflected photons, seismic echoes, the shared calendars of migrating animals. Laser bounces from mirrors left by brief human visits. Those relations make records. The records agree across observers. The agreement holds against noise. That is solidity enough for lives that must be lived day by day. And beneath that solidity, the quantum grammar hums possibilities flowing into facts, correlations doing work, symmetries keeping faith, quiet, exact, inexhaustible. Where this all goes next is not a riddle to solve tonight. More sensitive clocks will listen to smaller bends in time. Better qubits will hold phases longer. Spaceborne links will learn to pass entanglement between sunrise and sunset. Theories will trade edges, borrow lemmas, pair assumptions. Some puzzles will thin to clarity. Others will arrive with soft shoes to replace them. The work will be careful, the pace unhurried, the surprises earned. For now, let the questions close their eyes a little. The equations know their lines. The instruments will be waiting in the morning. Reality is not offended by our curiosity, and it does not rush to be final. It has always spoken in patterns, and we have always learned by listening. The night holds, the room is warm, and the story strange, exact, familiar, fades to a gentle hush.